probably let's get started. So yeah, welcome everybody to today's One World Probability Seminar. So it's a great pleasure to have Marcel Ortgiese here from University of Bath, who will tell us about preferential attachment networks with fitness. So Marcel, here you go.
Great. Well, thank you very much for the invitation. Yeah, it's a great honor to be speaking here. So yeah, I'll be telling you about preferential attachment networks. This is a joint work with Bas, who you'll be hearing like in an hour. Obviously, he's no longer in Bath. Unfortunately, he's now in Augsburg, but I'll update that. All right. So I'm going to be talking a little bit about preferential attachment networks first. So I'll be talking about a bit of general stuff. If you've seen preferential attachment networks before, a lot of it will be familiar. But I thought I'll take the opportunity to sort of introduce it in a bit greater generality as well. So obviously, what we're trying to find here is some sort of model for realistic networks, and sort of randomly pick this picture of the internet, so the actual sort of structure of the internet, all the routers that are connected, and that's sort of visualized in this OWPS project. I think the website's no longer up to date, but I still have the picture. And the thing I want you to sort of focus on here is that the networks we're trying to look at are very inhomogeneous, right? So you sort of see here these big hubs that have massive degrees, they have lots of neighbors, and they're sort of very structures at sort of all scales. There's sort of lots of vertices with tiny neighborhoods and many with absolutely massive neighborhoods. And so we're trying to find a model that can reproduce that. Okay, so that's our goal, formulate a mathematical model that can explain these typical phenomena. And what kind of quantities are we interested in? What are we trying to sort of mimic in a way? Well, the first one is, the most basic one is the distribution of the degree. Like, take a typical vertex and ask how many neighbors does it? It gives me some distribution, and I want to try and understand that as that, our network gets big. Another question that might be interesting is, what's the vertex with the largest degree? Like, which vertex has the most neighbors? And the other point I'll be addressing, at least in this talk, is typical distances. So if I pick two vertices uniformly at random, how far are they away? And what do you see in real networks? What do our models sort of do? And so I'll be introducing this preferential attachment framework in a sort of standard setting first. And then what I'm mostly interested in sort of will be sort of perturbing this model by adding a random perturbation to, well, the attachment rules. I'll make that more precise in a minute. And then the question is, how does this random perturbation, how does that change the phenomena that I observe? Do things change? And obviously that will depend on how strong the perturbations are, but can we quantify that? So that's the main focus of this talk. So I'll start by, okay. So maybe I can say a little bit more about degree distributions, because then we can address that on the standard preferential attachment first. So as I said, the degree distribution describes, if I take a uniform random vertex, how many neighbors does it have? And so pk will be the proportion of nodes with degree k. That sort of captures the same thing. And just for historical reasons, I sort of taken these pictures here from this famous paper by Marcel and Albert. And what these pictures were supposed to show, they took sort of three networks. So an actor collaboration, the World Wide Web, and a power grid. And every time you look at this, this is sort of, you plot these PKs on this log scale, and what you sort of see is a straight line. And so what does that mean? So log PK is a straight line. I can write this as log PK is equal to minus tau log K, some constant. And so that means the PK decays like a power law. There's obviously some controversy around, whether you can really observe these in real life, but I'll ignore that for now. This is sort of good enough for me. So I'm looking for a random network model that models this, that has these power law degree distributions. And what's special about preferential attachment model is that these power laws are not something that I'm superimposing on our model, at least in the classic sense, but something that sort of comes out of it. So this was sort of popularized by Marcel and Albert. There's some earlier works that have similar models, but this is sort of the paper that sort of blew up. And how does it work? Well, so this is one formulation. There are sort of minor variations of this, but they all sort of mostly lead to the same things. So I'll start with one node, and I'll sort of attach like a loop to it. And then my rule is that at time n+1, I introduce a new node, a new vertex n+1, and I connect it to this old vertex, to one of the old vertices I, with probability proportional to the in degree of that vertex plus c, some constant c. Okay, maybe I'll do a picture so that it becomes a bit clearer. So nothing happens in the beginning, so now it gets interesting. So let's say we've got this network onto two nodes, and this is sort of connected. I'm treating every edge as directed from a new vertex to an old vertex. And so at this point, at this time 3, this vertex here, oh yeah, I'm taking c is equal to 1. So this one has in degree 0, but because I'm adding a c, the probability to connect to 2 will be proportional to 1, whereas this one has in degree 2, so I'm treating this self loop as sort of being directed to myself plus this constant 1, so this the probability will be proportional to 3, so I'm connecting probability 3/4 to 1 and 1/4 to 2, right? So this is standard preferential attachment. A lot of you will have seen this before, and then sort of I update, I maybe connect 3 to 2, and then the probabilities change. And the effect that you observe is that if you already have quite a high degree, then the probability that you connecting to this one will be obviously high. So there's some sort of self-reinforcing going on here. So, as we've updated our network, now the probabilities, this one will be proportional to 1. This one has as in degree 0, this one has in degree 1. So +1 is proportional to 2, and so on. This one will be proportional to 3. And so you see this sort of effect that those who already have a high degree will keep getting higher and higher degree. And okay, yeah, sorry, that's maybe very, very, very long example here. So if you sort of model this, a simulation, so now you just, you simulate this, and what you get is that something that looks promising in that this network has vertices with very high degrees. So it develops these hubs and it's inhomogeneity that you expect to see. You can obviously formulate this as a mathematical result, and this was done sort of a little bit later. Lodewijks and Al were sort of the first ones to formalize this mathematically. And so what's the result? So you look at the proportion of vertices in degree k at time n, and then this proportion converges to some pk as the network becomes larger and larger, and this pk has a power law. And the power law is given as 2 plus this constant c, which was sort of the constant I had when I described the probability of heading to yeah, I've sort of cited Remco's book as well, which gives an excellent overview of this topic. And I think maybe this general result was sort of proved there, maybe for the first time. I think so. Good. But there are sort of very specific models that have been treated earlier as well. So this model gives you a way of getting power laws. That's sort of the first takeaway message here. And so these models can explain power laws, and that's why these models became so popular over the last, I don't know, 20 years. Good. And so the general belief in these networks and generally in random graphs is that this exponent in the power law that you observe sort of determines a lot of these properties. So there's always this question of universality, and it's believed that many properties are determined by these power laws. So they're really an important statistic of your network. Oh yeah, okay. So you can sort of ask more refined questions about how quickly you converge, a bit of advertising there for some other papers. Okay, so but what's the question we really wanted to ask is we want to sort of perturb this classic model. This has been studied for a while. It's very well known, and the question is now, how robust is this model if I now perturb my network? And one point I want to address with the model I'm presenting here is that in preferential attachment network, if you come in, everyone's sort of the same. Everyone has the same initial fitness, right? No one's special. And this whole thing comes sort of just out of this fact that if you sort of by chance happen to have a high degree, you get a higher and higher degree of self-reinforcement. But there's nothing about vertices that's sort of different apart from when they come in and how much time they've had to But what if that's not the same? Maybe you're thinking about, I don't know, some websites, maybe some very old-fashioned, or something, where you provide better content, and maybe you're a lot more likely to capture links because of that. So then you can think about having an initial sort of perturbation of your attractiveness, so that the rules are no longer just everyone gets treated the same in principle, but there is some random fitness associated to each. Okay, so we model this by just associating an ID fitness to every vertex as it comes in. And then there are two possible, well, there are two standard ways. There are obviously lots of other ways, and Bas will come back to this in his talk. There are two standard ways to put out the preferential attachment probabilities. So the first one is preferential attachment multiplicative fitness. So this is due to Bianconi and Barabashi. And the change now is that vertex n+1 connects to vertex I with probability proportional, not just the degree, maybe that's constant, but the degree is multiplied by the random fitness. Yeah, okay. Maybe you shouldn't take the integer. So you get started. So you multiply by some random fitness. So that's quite a drastic effect in a way. So if you sort of have quite a high degree, then your fitness is 2, then everything gets multiplied by 2, whereas other people maybe don't get this multiplied. And the second model is to add a random fitness, right? Sort of things you can do by adding noise, either multiplicative noise, additive noise, if you're thinking about speed or whatever. So this is what we'll be doing. So this is, I guess, was proposed in this paper by Ergin and Rogers in 2002. And the rule changed so that vertex n+1 now connects to vertex I with probability proportional to in degree plus some fitness. I'll be more specific exactly what I mean in a minute. Good. Okay, I just wanted to mention this model A because it's sort of one way of perturbing things, and that leads to a very interesting maths, but sort of also very challenging maths, and particularly leads to this phenomenon of condensation. So say your fitness is sort of bound by something, well, you can observe in these models that in a certain condition, a positive proportion of incoming edges connects to vertices that are closer and closer to the essential supremum of the fitness. So there's sort of, in a way, they sort of vanish this, and by Bianconi and Barabashi solved this Bose-Einstein condensation, and it's never a good idea to ever mention this in your talk, so because it leads to lots of discussions. But so there's sort of a lot of literature on these related models that have this condensation. That's super interesting, but also quite challenging. Yeah. So we'll focus on the maybe slightly easier case, of preferential attachment with additive fitness and see what we can see. Good. All right. So yeah, let me just remind you of my model just to be precise, because so you have ID fitness and vertex n+1 in comes in, and then it connects to exactly one vertex, one old vertex with index less than, with probability proportional to the in degree of that vertex plus the fitness. And what we'll be doing later on is we will be changing the model slightly so that when this one vertex comes in, it has out degree m, and then each of these m stubs independently connects to one of the old vertices, to exactly one old vertices with this probability. And then each half edge does that independently. Yeah, there's sort of lots of different ways that you could modify this a tiny bit. Like you could say, okay, connections for each of these, I don't know, you do it independently, you get a random out degree, and as long as the average is m, you get very similar results. I think by now there's sort of fairly robust techniques to analyzing these models. So the exact specification doesn't really matter too much for most of the results. Well, maybe not everything. Good. Okay, so but for now I'm going to keep the out degree at 1 because for the first few questions it doesn't actually change too much, and it'll just be an extra parameter hanging around. Just to mention, there's a related model by Dav et al, where rather than having this extra fitness, you just say vertex comes in and has a random initial degree, and then you do preferential attachment with that. But they're sort of different because for us, the out degree is typically fixed and equal to them. But you can observe similar effects there as well. Good. All right. So why are we interested in this additive in the case? Well, you can think of it as a random perturbation, but something that's also sort of interesting is that in classic preferential attachment, we'll come back to that in a minute, the largest degree is one of the old vertices. Just by hanging around for a long time, you can get a massive degree, and none of the young vertices can outcompete you. But then I guess if you think about, I don't know, your favorite network, and maybe you want to have a mechanism by which younger vertices can outcompete the old ones just by being more innovative, like having, high innovation, having more attractive content, that kind of thing. So we want to also sort of test that a little bit. How can this initial attractiveness, can we sort of tune our models so they compete with the old stuff? So that's the main question we want to answer in these ones. Can we sort of start a competition? Can we sort of outcompete the old ones? Yeah, by the way, if you have any questions, please feel free to ask. I don't type in the chat or ask. I don't know. Cool. Hope that's clear. All right, so what's the first results? The first results often is for our model is degree distribution. So this is our joint work now a few years back. And it says that if the mean of your fitness is finite, then you get almost sure convergence of the proportion of vertices that have a certain in degree, say equal to k, that converges to some UK. And the interesting thing, well, the next question is, so what does that mean? Can you analyze the UK? And what's the tail experiment, right? So earlier I sort of briefly mentioned that in networks, the tail experiment is the thing that should tell you everything about the network. So what is that in this case? And the interesting thing is that you now observe two phases, at least two phases. So alpha, I should have said that. So I'm assuming here my fitness is fairly heavy-tailed, so that I can compete with the preferential attachment mechanism. So I'm assuming that the probability that fitness is some bigger than some x decays polynomially, and it decays like x to the minus alpha plus 1. So if it was integer valued, probability is equal to x, decays like x to the minus alpha. Good. Okay. And so by choosing alpha relatively small, I've got very heavy tail fitness distribution, so I see quite large values of the fitness. So but if alpha is large, then it's fairly light tailed. So in that case, I just see that the mu k, the decays like k to the minus 2 plus the expectation. And so if you compare that with classic preferential attachment, that's just like you replace the random fitness by its expectation. And that was this constant c that I had in my first slide. And if you do that, then you get exactly the same text. Right? So this is sort of the regime where the fitness is relatively well behaved. You can sort of average it out. The effect is the same as having constant fitness equal to expectations. But if you make the fitness more heavy-tailed, then the tail exponent changes, and it's sort of driven by the fitness, and it decays like k to the minus alpha, which is the same as the largest fitness. Okay, we will make that more precise. So that's sort of two regimes, and there's a third regime, which is when alpha doesn't have a finite expectation anymore. So alpha is between 1 and 2. Then, in fact, the in degree is with probability tending to 1, high probability, uniformly chosen matrix has in degree 0, so no one attaches. Okay, so that's very different. And I'll come back to this at the very end of the story. Yeah, okay, cool. And so to prove these results, as I said, there's reasonably robust methods for this. We use stochastic approximations based on this joint work with Stefan that we did a while ago, which is sort of a way of making like the master equation that maybe theoretical physicists would write down and turning that into a difference equation with some noise, sort of like a discrete ST, if you want, and analyzing that. That's proved to be quite a good tool in this area. So yeah, just maybe to this classification about weak and sort of strong effects of the fitness. So we've got an explicit distribution expression for this mu k that you probably didn't want to see. But here it's anyway, and you can sort of do some Taylor syntactics of this, some tail analysis. It's analysis, and you get what I said. But what I just wanted to emphasize with the slide is that so if the fitness is relatively well behaved, no extreme, not too extreme, then the fitness effect is negligible, and I'll call that the weak disorder case, coming from some random environment kind of terminology. And if alpha is between 2 and 2 plus this expectation here, when the fitness has a strong influence, then I'll call that strong disorder. So the initial randomness has a strong effect in that case. And otherwise, if the fitness distribution is very heavy tailed, then the fitness completely dominates. I call it extreme disorder. I'm trying to stick to this terminology. Good. So we've sort of understood the tail. We've understood the empirical distribution. So we know for a typical vertex how many neighbors it has. And we know this tail exponent, and so now the tail exponent should tell us everything about the models. So we sort of have to go away and check that. So the next question would be, what's the largest vertex? What's the most powerful vertex in our network up to time n? Okay, so I'll remind you what's known for the classic preferential attachment model. So for the classic preferential attachment model, so you attach with in degree plus some constant. So tau is the power law exponent 2 plus c, and then the largest degree behaves asymptotically like n to the 1 over tau minus 1. Okay, and the other bit of information is that the largest degree is one of the old vertices. So one of the first few vertices that sort of comes in, just by chance, picks up the most incoming connections. And so, okay, good. So the question is here now, does the same work for us? Okay, my tau looks slightly different, right? I've rewritten it slightly. Either it's alpha if I'm in the strong disorder case, or it's 2 plus the expectation if I'm in the weak disorder case. But do I get the same behavior for the max degree? And the answer is sort of. So the largest degree does behave like it should, like it increases like n to the 1 over tail exponent minus 1. That's exactly the same thing. So I'll start with the weak disorder case here. And in the weak disorder case, it's exactly the same as the preferential attachment. It's like you replace the fitness by its average. Again, the most powerful vertex is one of the first few, one of the old vertices, and it depends. It grows, the largest degree grows like it should in the normal classic preferential. However, if you go to the regime where the disorder is strong, then the tail exponent still gives you the right answer for the growth of the largest degree. So it grows like n to the 1 over alpha minus 1. But what's different now is that if you try to find where this new vertex is, it is of order n. Okay. And then finally, if you're in the extreme disorder, then the largest degree grows like n, and you can find it as of order n, one of the new vertices. Well, where does this come from? Well, it obviously comes from the fact that in the strong disorder case, what's important is having large fitness. So if you just ask how does the largest fitness grow as up to time n? Well, it grows like n to the 1 over alpha minus 1 in that case. So you see that the largest degree just grows in the strong disorder exactly like the largest fitness. Okay, so it's one of the more recent vertices that just by looking at a larger number of vertices, you obviously get larger fitness values. So good. So you see there's a real big difference between the two systems. If in the weak disorder, it's like classic preferential attachment, and in the other, in the strong disorder case, really driven by large fitness values. We can make that a little bit more precise statement, and I think there's a little bit, the first, in the weak disorder, this is sort of the statement that's known for the classic preferential attachment. So if you're asking for the index of the largest, that corresponds to the largest degree, that converges to some finite random variable. It's one of the old vertices. And you can use martingale techniques to show that. So if you rescale the largest degree by the right thing, it converges to some martingale. Good, but in the strong disorder case, it's slightly more interesting. Maybe, yeah. So if you take the index of the largest vertex divided by n, that converges to a random variable, and the largest degree also, but taking the rescaling coming from the largest fitness also rescales. The interesting thing is that the limit has sort of a not completely trivial structure, and it's given in terms of some Poisson point prices with a certain intensity. That's not surprising because that's what you get for the largest fitness value. But what's interesting is that it's not just the fitness value itself, but it's some functional which sort of incorporates this competition between coming in early and having large fitness. Come back to that in 2 seconds. Good. Okay, so in order to prove this, we use a classic technique in preferential attachment, is this Morris martingale, and you can use it to show that there's some sort of normalization. If you take the in degree plus the fitness and normalize it appropriately, then you get a martingale. If you get a martingale, oh yeah, and this constant here behaves like n to the 1 over theta, and this theta is 1 plus the expectations. Yeah. So what you get from that is martingales obviously have constant expectations, so you get a formula for the expectation, the expected degree, if you just condition on the fitness. And what you get is that it's sort of some martingale term divided by n to the minus 1 of theta minus the fitness. So if you sort of work this out, what you get is that the expected degree is essentially the fitness multiplied by a term which looks like something from the classic preferential attachment term. So it's n over I to the power 1 over theta. So if I had constant fitness, this is exactly what I get for preferential attachment. But the effect of the additive fitness is now that I get a multiplicative constant outside. So that's kind of important if you want to understand these models. So the effect of the additive fitness, yeah, becomes a multiplicative. That's good. Okay, cool. So how can I use this to answer, sort of analyze this question of what's better? Is it better to come in early or late? Well, if I just look at the expected degrees of conditioning on the fitness, but looking at the degree of that, then if I look at it up to some time k, I want to see if that's a good scale to come in, then the largest fitness I see grows like k to the 1 over alpha minus 1. So if I replace the fitness by that, then I get a term k to the 1 over alpha minus 1, and I get a k down here. So I get a sort of a prefactor that depends on when I come in, k to the 1 over alpha minus 1 minus 1 over theta times some constant a. So if I want to optimize now, I have to, it depends on whether 1 over alpha minus 1 is bigger than 1 over theta or not, right? That tells me how to choose the optimal k here. So in the weak disorder case, it's when alpha is bigger than 1 over plus theta, then in order to make this as big as possible, I want to take k of order 1. And so in that case, you can see from this conditional expectation calculation that that preferential attachment mechanism dominates in that case. And it's best just to take one of the old vertices, even if their fitness is completely, useless. Right. And in the strong disorder case, you get the opposite, right? So then then it's best to make this term here as large as possible. So you take k of order n, so some constant times n. And you can be a little bit more precise in this case and sort of get the scaling limit out of this as well. So if you were just to look at the values of the maxima of your fitness up to time n, you can extreme value theory tells you that if you sort of calculate a point process where you record when this fitness occurs and what the value is, everything rescaled, that converges to some Poisson point process. And so you can write this conditional expectation in terms of this Poisson point process, right? So the conditional expectation properly normalized gives you some fitness term normalized and some term that depends on when you come in, so by this n over I term. And then you apply that by some one of your points in your fitness, in your Poisson process in the limit, and then you can sort of see this functional pairing of multiplicative constants and fitness. But you also get a bonus for coming in early, right? So there's some sort of competition. Height fitness, which will occur for the t larger, is competing with coming in early on this timescale n. When you get more bonus from the preferential attachment mechanism. Okay, so when I say, so the strong disorder case is sort of interesting because it really balances the preferential attachment with the extreme values of the fitness in a non-trivial way. Cool, good. Any questions, please just shout. Yes. All right. So the next question is, okay, so we understand what the typical vertex, what degree it has. We understand what the largest degree is. And maybe in the next classic question you can ask about the structure of these networks is what are typical distances? And again, I'll remind you of what's known for classic preferential attachment. And the sort of motivation for this comes from this observation that in real world networks, you typically observe very short distances. And when I say distance, I mean I pick two vertices and I count how many edges are sort of on the shortest path between those two. And so I just picked an example. So Facebook network from 2012, people looked at these degrees and they sort of found that the distance is around 4. And you may have heard of 6 degrees of separation. That's sort of the same phenomenon. So distances are really, really short. How does this get reflected in classic preferential attachment models? Does these really short distances, are they somehow reflected? Okay, so there's sort of, I guess, yes, sort of the case, well, I'll go through the cases in a minute. So that's pretty much understood, and it depends on the power law exponent tau. So in the case when the power law, when the degree distribution is quite light-tailed, the distances are log n, which is not super short. And then if it's tau equal to 3, so sort of critical case between, then the distances are order log n over log n. But if you're quite heavy-tailed, if tau is between 2 and 3, you get distances of order log n. And log n is, for real size networks, pretty close to constant. In terms of sort of who proved what, I guess the Lodewijks and Riordan, sort of, that's the first thing they just had the C equal to 1 in my model formulation, so they always were in this case tau is equal to 3, at least in the beginning. And then Domus et al. Proved the log n result, and they proved, I think, log n bounds, but maybe not the right constant, which I didn't put down here, as due to Dirac. No, actually, I forgot. Dirac mentioned that. Oh gosh, forget it. Sorry, not great. Okay, so one of these pictures is reflected in our one. And so this is sort of a theorem in progress. So you should take it with, well, okay. Well, we're working on it. And the result is, it looks sort of, it's what you expect. And so if you're not too heavy-tailed, then distance should be of order log n, although we haven't quite ironed out all the details. But if you're between 2 and 3, if you're quite heavy-tailed, your degree distribution, you get log n's. Actually, I should mention this before I forget that. In this model, it's really important that the out degree is at least bigger than 2, and I'll become clearer on the next slide. So I'm now dropping this assumption that m is equal to 1. I'm going to the case where m is bigger than 2. But then the tail exponent changes slightly, so you'd have to divide the fitness by m, but nothing else really changes too. So what it tells us, in a way, the order of distance is universal. So log distances are the same as in the sort of classic preferential attachment model, and as sort of to some, without the exact constant, are similar to a configuration model where maybe a local neighborhood's the golden Watson trees, and that sort of explains your log n, right? If you sort of have a tree that doesn't, if you look at a uniform vertex, look at its neighbors and so on, then you get this local neighborhood, and that's a tree in all of these models, but in a configuration model, it would be golden Watson trees, so you know how quickly it grows exponentially fast. And that tells you that in order to reach any other vertex, you essentially don't have to go further in log n distances. What breaks down here is that if the tail exponent is between 2 and 3, you do no longer have a well-behaved golden Watson process in the sense that it has like a Malthusian parameter or whatever. So it doesn't, your branching process sort of, I guess, is that an explosion? But it sort of grows much faster than a branching process with finite mean. So that changes here. And why is it at 2, sort of the distance at 3 and maybe not where the variance changes? Well, it's because when you think about degree distributions, you have to remember that you sort of have a size bias distribution that you really should be looking at, because you're starting somewhere and then you're asking, well, what's the distribution of one of our neighbors? Well, I've already connected it. So that sort of means I should be dealing with the size bias distribution. So the difference between really short and the log n and the sort of short log n behavior occurs at tau is equal to 3, where you so it's not exactly where you think it should be. It's where you lose your variance. Did that make sense? Hopefully that made sense. Okay, good. So our proof sort of follows, at least for the log bounds and the log lower bounds, we follow Thomas et al., and then we follow Dirac and Martis for the other case. So what's the picture that that you should have in mind? And without the fitness, there's sort of a similar thing for classic preferential attachment. So the idea is, and I focus on the case of log n distance here, just because that's maybe the more interesting case. So the idea is that you sort of decompose your network into several layers. And so you have your typical vertices, that's sort of this layer down here. In our case, they arrive quite late. Fitness is not particularly large. That's, typical vertices in some sense. And then there are lots of vertices there are some vertices in your network that are sort of special. And for us, they can be special in two different ways. Either they could be born quite early, which means they sort of naturally have a high degree, or they could have high fitness. And so I guess that's what this sort of picture is supposed to illustrate. We have these sort of layers of more and more special vertices that become more and more powerful. So I've plotted them in green here. And so you now want to understand what's the distance between two uniformly chosen vertices. So my U and Bn. Those are just standard vertices. They fall down here. They're coming in late. They don't have particularly high fitness. So what do? Well, they connect to one of these more powerful vertices because you've got a high probability to connect to one of those. And okay, you connect to one. That's sort of the first step. Then you try and connect this layer to one layer up, which is even more powerful vertices. And in order to do so, you need these connectors. So you find a typical vertex, a red vertex here that you can, sorry, maybe my color's not great, that you connect to go to this next layer. And then you keep going. You just always go via these connectors in the normal vertices to go to higher and higher layers in this construction. Until you get to a point where all the vertices sort of have distance 2. So in this highest layer, everyone is not directly connected, but connected via one connected on here. And then you sort of make your way back down through the layers until you reach your vertex. And this sort of picture is, it's used in classic preferential attachment models. Similar stuff also works spatial models, this kind of things you have to think about. So this sort of skill is, I guess, in these models, how you define your layers. And what I'm sort of hiding a little bit is maybe that, we have one tail exponent, but there's sort of two different ways you can get this tail exponent, either through high fitness values or high degree. And you have to sort of tune things quite carefully, and you have to make sure that say, if you're in the regime where you've got high fitness, that the vertices with high degree don't sort of throw you off. And that's the sort of subtle bit that I'm not going to tell you about. Maybe also sort of more technical bit, but it's the sort of picture that's known for classic preferential attachment that also works here. Maybe one small point that you're familiar with it, if you've seen some preferential attachment model. It's like if you compare this to a configuration model, so a non-dynamic model, you also get these different layers, but the difference is that you don't need these extra connectors to get to the next layers, is that these layers are just directly connected to each other. And so you lose a factor in the configuration model, you don't have this extra factor 2 that we have here. Cool. Okay, so at first glance, the model looks very similar to what's known, but it's sort of getting these details, this balance between fitness and preferential attachment right. That's non-trivial. Okay, cool, good. So that's sort of the picture for the classic preferential and not super heavy tail case. There is this regime of when the fitness doesn't have any first moment. So expectation is finite. In that case, if you look at the sum of the fitness values, which naturally occurs when you try and normalize your probabilities, there's no law of large numbers anymore, but instead you get sort of a stable law. So you have to rescale the sum, not by 1 over n, but by n to the 1 over alpha minus 1. and then you get a random constant. So that's much bigger than order n. So that changes things. So these connection probabilities look differently now. So I've actually written this down, but now I'll write it down. So the connection probability for a new vertex to connect to another vertex is just n degree plus fitness, and the normalization is hopefully n plus the sum, modulo some constants now. So you see that the sum here plays a really important role, and in this extreme disorder regime, these probabilities, this n you can forget about. In fact, you can forget about the in degree here as well. They can't compete with the fitness. So it's essentially just like you choose an null vertex with fitness proportional to its fitness. You can still do some of the things. You can, for example, still look at the maximal degree, but now it's a slightly more complicated function of the Poisson point process, because you sort of have to take these sums here, which luckily also converge on the same scaling as the fitness, but you sort of have to take these into account as you build your maximals, as you choose. Yeah, as I said, the degree of the preferential attachment becomes irrelevant. So what happens for distance in this case? That's, I guess, what I want to tell you about. Well, the distances are now of order 1, and in fact, they're either 2, 3, or 4. So, and that's very similar to what's happening in the configuration model, where typical distances are either 2 or 3. That's right. And how do you see this? Well, in this model, essentially only those vertices with really high fitness matter. And I guess if you want to know at time n who you're connecting to, then maybe you look at those hubs where the fitness divided by normalization is bigger than some constant, some small constant. And then what can happen? Well, either vertices u and v both connect to the same hub, because all you're going to connect to are hubs. So the question is, both u and vn could be connected to the same hub, in which case you have distance 2. It could be that they connect to different hubs, but the hubs happen to be connected and they get distance 3. Or you can connect to different hubs, but those hubs are not directly connected. If they're not directly connected, there's definitely, with probability 1, one young vertices that is connected to both. So then you get distance 4. And in fact, you could probably write down the distribution of this, but in terms of Poisson process, but we haven't quite worked out the details. So it's a very sort of different picture. It's a very extreme disorder, and really only having really, really high fitness matters. Okay, cool. So anytime, any questions? Good. Okay, so then the last few things. So slowly running out of time, but I got like a few minutes. So this is going to be pretty brief. I just wanted to sort of advertise tangent that we took at some point in this project, which I thought turned out to be really interesting. So in this case here, preferential attachment, you always attach with probability connecting to in degree plus this fitness. But as you saw in this extreme disorder case, in that extreme disorder case, the degree doesn't actually matter. So what happens if you just take a model, you do a dynamic model, but every time you connect with probability fitness proportional to its fitness? Okay, so you take a IID sequence of fitness, and n plus 1 connects to vertex I with probability proportional to fitness. And this is sort of a generalization of a random recursive tree, where you just bring in a new vertex and connect to one of the all vertices uniformly. You can make it a tree, you can make a graph, doesn't matter. But these sort of have been studied intensively in the sort of deterministic setting. There's also some sort of work on this when you have extra weights. But a lot of our techniques sort of work. Degree distributions sort of immediately translate. Asymptotics for maximal degrees still work, but now it's interesting because you don't have this preferential attachment effect anymore. If you want to understand the largest degree, the sort of exact asymptotics of the fitness, how the largest degree grows, makes a more important, plays a much more important role. And so we've got some results on quite heavy tail distributions, describing the maximal degree, and we've got some results also together with Slava on boundless fitness distribution, and Bas has a follow-up paper on that as well. So we sort of have some detailed understanding there, but what I want to point out is that surprisingly for us at least, was that things are sort of less, well, in a way, the preferential attachment, you don't have this competition anymore. So you need to understand sort of the fitness distribution much more carefully. And in fact, there's still an unopened, an unresolved regime here between the boundedness and these heavy tail distribution, where you sort of have a lighted distribution, where at some point, sort of, yeah, I don't know, I guess at some point, this sort of mechanism of random recursive trees, the way you sort of, the fluctuations that you get there will sort of overtake the random fluctuations you get from the fitness. And this regime is less well understood for us. So we're still okay. Just I think, yeah, actually time is all right. So just to wrap up, as I said, multiplicative models are super interesting. Loads of work on that recently, although I think there are sort of remaining challenging things. Good. In the weighted random recursive tree, I just said there's some sort of regime that we've not looked at. And you can sort of play with these models and take general functions of weights. I think spatial models sometimes share some of these features with these fitness models. It's of interesting stuff. And there are lots of people looking at this. So and yeah, you can play around with this fitness function. I only looked at this additive case, and Bas will be talking more about other choices you could make to connect degree and the fitness. Right, I'll stop here. Thank you very much.
Well, thank you, Marcel, for a real nice talk. So we have the time for questions. So if you want to ask a question, just as usual, feel free to unmute yourself or just raise a hand or put it in the chat. I think, Peter, yeah, just go ahead.
Yes, so I hope you can hear me again. So I'm obviously sort of approaching this very much from the spatial direction because that's what I'm the most familiar with.
Mm-hmm.
There, one way you can sort of look at things is, of course, that you look at a finite box, but your Poisson process is sort of realized on all of Euclidean space, and then you're making your box bigger and bigger. And when you do it that way, of course, you will find vertices that sort of, in that case, they don't have age, they have a mark.
Yeah.
But the marks are not sort of coming uniformly as age, but you find sort of older and older vertices as you're increasing your space, which sounds very similar to this example now at the end, where you said you sort of turn off the preferential attachment part,
Mm-hmm.
just sort of have these additional fitnesses. So would you expect that this would essentially behave sort of like a non-spatial version of that, because you lose the ordering, but otherwise, presumably, you retain other properties?
Yeah, maybe. I've not looked at that, but yeah, I guess so. Yeah, it could be. It does. I agree that it sort of shares this feature. So yeah, we should talk about that. Sounds yeah.
Thank you.
I guess next, Sina Reinhardt.
Yeah, thank you, Marcel, for a really nice talk and quite comprehensive. I remember that the Bolobus and Riordan, they have got this LCD model, which is slightly different from the one which you described. Does it make a difference at all?
So I mean, a lot of like degree distributions or something, I think there's sort of so many robust techniques that sort of minor details don't matter. I don't actually remember the details of the LCD model, but I think if it's sort of in this sort of class, you know the probabilities to connect, you have some sort of conditions on, I don't know, that, well, you can sort of formulate some general conditions on that, for example, that give you degree distributions, and then it doesn't really matter so much.
I mean, that's a model which allows self-loops.
Yeah, okay, yeah, for example, that's fine. Yeah, self-loops are not a problem. That's sort of, you can do with stochastic analysis. With stochastic approximation techniques as well, that's fine.
Okay.
Yeah.
Thanks.
Yeah, that wouldn't matter. But okay, it depends. If you're asking finer questions, it might make a difference. But like degree distributions is super.
Yeah, we're thinking of shortest path.
I think like some of the stuff is quite robust. Like this, I think the paper by like you mentioned, Mertes sort of tried to formulate things in a quite robust way. But yeah.
Thanks.
Yeah.
Okay, I guess a follow-up, Peter.
It's not really a follow-up. It's a separate question from earlier in the talk. when you were given sort of these, or when you showed us these three regimes you get, let's say, in the degree distribution, right?
Yeah.
And the how was it called? Strong disorder and extreme disorder.
Yeah.
So of course you gave us sort of the order of let's say the age of the highest degree vertex. Can that be made any more precise, or is there a distribution that one could sort of get about how old the highest degree vertex actually is?
Should I go back to this? Yes. So yes. So
Because I mean, obviously, if it has a very high
yeah.
fitness, it will start immediately collecting vertices, but before that becomes of order n, it will take a while, right? So it will no longer be the youngest vertex. It could be in the first 10% of vertices by the time it accumulates.
So it sort of comes into this functional, right? So you could try, I don't think we've done that. So you could try and figure out if I give you a Poisson price with this intensity, where is the maximum? We didn't
We
try
have done
that
it.
down did we, Bas, or did we try
Yes,
that?
we did, yeah.
I did write it down. Oh gosh.
Yeah, so in the strong disorder regime, we have an explicit distribution for I and Z.
Yeah.
If I remember correctly, I think I is some beta random variable to some exponent, where all the parameters depend on the model parameters. And Z has something to do with, no, that I can't remember. And in the extreme disorder regime, we also have an explicit formula for these I and Z in terms of this point process, but there's no chance for, or we were not able to say anything more than that.
That's quite hardcore in evaluating.
Yeah.
Yeah, but it's sort of a Poisson price, right? So you can write it down certainly, but then can you recognize it's something? But yeah, I guess.
Okay, so but you essentially have much stronger results than just knowing the order of them.
Yeah.
Yeah. Although I think just having it as a picture of the Poisson prices says a lot more. But yeah.
No, of course.
Yeah.
Okay. Thank you.
Okay, all right. Any more questions? Comments? Okay, doesn't seem to be the case. So thanks, Marcel, again.
Thank you.
And let's maybe do a short 2-minute break before continuing with Bas. So yeah.
Thanks.
Okay, this bus running away. That's already a sign for should make the break. All right, let's see if I can share. Yes. You see this? That looks very good. Nice, perfect. So let's maybe wait for a second for Peter and Marcel to return. Yeah. Then
Is Tejas still in Berlin?
yes, he's still in Berlin. Yeah, I think he recently
renewed his contract by getting more grant money within VIAS, so he'll be there for another 2 or 3 years if he wants, I think.
Very good. All right, so shall we get started?
Yes, sure.
Okay, cool. Then yeah, let's go for the second part with Bas Lodewijks from the University of Augsburg, who's going to tell us about structural properties of superlinear preferential attachment trees for fitness. So Bas, here you go.
Thank you very much, Dominic, and welcome back, I suppose, or welcome if there's anyone new joining. We're going to shift gears a little bit in this talk. Everything is still going to be around these preferential attachment models with fitness, but rather than the linear case that Marcel discussed, we'll now look at the superlinear case. And though some intuition and ideas will be similar there, other things will also change quite drastically. In particular, the way that we analyze this model and the way we think about this model will be completely different from anything that Marcel talked about. So really a hopefully sufficiently different talk. And most of what I will discuss today is joint work with Tejas Iyer, who's a postdoc at the Weierstrass Institute in Berlin. So yeah, let's go ahead. If I can. Yes, right. So I want to set up a little bit more of a general model compared to what Marcel talked about. So we'll take some function f, which we'll call the attractiveness function, and it takes 2 arguments. It takes the integrity of a vertex and the fitness of a vertex, which we'll think of as a non-negative number. And we'll take these fitness or vertex weight random variables wi, and then let a tree evolve as follows. We start with a root, then a new vertex will always connect to this root. And now vertex 3 has 2 choices. It either connects to 1 or to 2, and it will do so according to these probabilities, where connecting to, say, vertex 1 is proportional to this attractiveness function f, with arguments the integrity of vertex 1 and its fitness or vertex weight. And the same is true for vertex 2. So suppose that 3 connects to vertex 2. Now a 4th vertex comes in and has 3 options. And in particular, we see here that now the probability to connect to 2 has changed in the sense that the argument of this attractiveness function f in this probability has gone from 0 to 1 because vertex 2 has increased its integrity. Right? So, okay, maybe 4 connects to 2, and this continues on and on and on. Okay, so this is a general setup. You could choose whatever you would like for this function f. We want to think about superlinear preferential attachment trees, meaning that the function f grows superlinear in the degree. What do we mean with superlinear? It is that this summability condition is satisfied. So regardless of the value of the second argument, if you sum over the first argument, then this function f should grow fast enough so that 1 over f summed over j is going to be finite. So for example, if f of j comma w would be, say, w plus 1, I hope you can read this, times j to the power p, or I should probably say j plus 1 to the power p, where p is strictly larger than 1. Okay, so if we then look at these attachment probabilities to connect to some vertex I when you already have a tree of size n, then what we notice now is because this function f is no longer linear, as was the case with Marcel's talk, this partition function, the sum at the denominator, is going to be random. Not just random because of the fitness random variables, but because the degrees, which are also random in this tree, no longer sum to something that is actually deterministic. And this is the reason why this linear case is fairly well understood, but many other cases there's not as much understanding because the randomness of this partition function makes the analysis much harder. And this is the reason why we will stick to trees throughout this talk, and we won't say anything about non-tree models, because there is some technique, some way, something that saves us, in which case we can still say something about these trees. And that is that we are going to embed this sequence of discrete trees into a continuous time branching process. And that works as follows. recall that we had this tree that we constructed so far, consisting of 4 vertices. We'll now assign to each vertex in this tree a clock, and the first clock that rings, that will be the vertex where we will make a new connection. And each clock will ring after an exponential time, which has exactly as rate this attractiveness function f with arguments the in-degree of that vertex and its fitness. So by the properties of the exponential distribution, the probability that, say, the clock of vertex 4 will ring first is exactly this transition probability that we had previously. So choosing these clocks in this way gives us exactly the right sort of transition dynamics that we had in our discrete sequence. So if this clock indeed rings first, then we attach vertex 5 to vertex 4, and we then give vertex 5 its own clock. We update the clock of vertex 4 because now its rate is going to change, and all the other clocks of all the other vertices that did not yet ring, we just refresh them using the same distribution. Okay. Now, a crucial observation is that refreshing a clock is the same as just letting it continue to run because of the memoryless property of the exponential distribution. So really, if you fix some vertex I, then what you can just say is I wait until the clock rings, and that will be the time at which this vertex creates a new attachment. So after these amounts of time, this individual will create attachments. If we rephrase this or look at this from a different perspective, you can just say that each individual I gives birth to a child after this amount of time. And now suddenly we're in the world of branching processes, where we no longer have vertices, but rather individuals, and rather making new attachments, individuals give birth to children. And so that is how our continuous time branching process is going to work. And to make this a little bit more precise, I'd like to discuss so-called Crumb-Modiagas branching processes, because this embedding that we just did in this branching process with these exponential interbirth times is just one example of a much broader family of continuous time branching processes known as these CMJ branching processes. So here we start with some root individual, which we assign this weight W indexed by the root, and we sample a point process. And the points on this point process will indicate for us when this individual gives birth. So here we have time that goes from left to right, and every time we encounter a point, we would create a new individual that is a child of the individual on whose timeline or point process we are. So if we move this to the right, then at some point we have a new child of the root, its first child, 1, which we give an IID weight and an IID copy of this point process, which we translate by the birth time of this first child. Then in time, the next birth that takes place is a child of this child 1, so say 1, 1. We again sample a copy of this weight and of this point process, and this continues on and on. So the idea is that, or the intuition here is that if an individual has a large weight, then they will be able to give birth to children much quicker than those individuals that have a small weight. So perhaps this root individual was very lucky and had a very high weight, and that's why these interbirth times here are fairly small, and we see many points on this line, whereas perhaps the individual 2, say, was very unlucky, had a very small weight, and therefore it takes a very long time even before we see its first child to be born. Yes, Peter?
I just want to make sure I don't misunderstand. So you are really working with a Poisson point process with a homogeneous intensity over time?
No, no. So it need not be even a Poisson point process.
So, but the rate at which, let's say, this root has points being birthed or whatever is not increasing after each point.
It is, yes. So here, if you really think about these exponential interbirth times, then the rate for the first interval will be 0, w, f of 0, w. But once it has given birth, the rate changes to f of 1, w. And then after the second birth, it changes.
Point process? I thought that that's then a birth.
No, no. So it is not necessarily a Poisson process. If you would choose this function f just to be, say, constant everywhere, then of course you would have a Poisson process. But if f really changes, if f is really dependent on its arguments, then you would not have necessarily a Poisson point process. But it still is some point process.
It is the fact that this is not a Poisson process then.
Yeah.
Okay, thank you.
Okay. All right. So if we sample this this genealogical process at some time, then we can of course create the corresponding tree that this branching process really has formed, because the root has 4 children, and child 1 has then 2 more children, 1, 1, and 1, 2. So that will look something like this. Okay, so to be able to continue from here, I need to introduce a little bit of notation, so bear with me. So these trees, we will label them according to the so-called Ulam-Harris tree, meaning that we have this root individual here, and then n to the k denotes all individuals in the kth generation. So the individuals in the first generation are the children of the root, which are labeled by 1, 2, 3, etc. Then the second generation are individuals like the children of 1, which are labeled as 1, 1, 1, 2, etc. And generally, any individual U will have children U1, U2, U3, and so forth. Okay, so given individuals in this Ulam-Harris tree, we now sample for each such individual U, first a weight, and then a sequence of interbirth times. So XUJ stands now for the amount of time that corresponds between the birth of child number J minus 1 and child number J of U. And in this embedding of our preferential attachment tree, we would choose these interbirth times to be these exponential random variables with these rates that depend on this function f. Okay, so given these interbirth times, we can construct the birth times of individuals in our Ulam-Harris tree. So the root is born at time 0, and then recursively we can say that an individual UJ is born at the time which equals the birth time of its parent, and then you have to add the J interbirth times, the time that the parents need to give birth to its Jth child. Okay, so nothing surprising there, I hope. And with these birth times, we can now construct a tree process. So this calligraphic T or math script T, not sure what it's called in LaTeX, is the branching process at time T, and simply consists of all individuals U who have a birth time that is no larger than T. So all individuals who are born by time T. Okay, so that is essentially the branching process and how we will view it over time. Some important quantities to further think of are these stopping times, tau k. Tau k is going to be the first moment in time at which this branching process is of size at least k. And then tau infinity here is going to be the limit of this sequence of stopping times. And finally, if we look at this branching process at time tau k, suppose that we call this the tree that we have constructed tk, then it turns out that because of this embedding that we used, that our preferential attachment tree of size k is exactly equal in distribution to this tree tk. So if you stop the branching process at such a stopping time tau k, then what you see is exactly your preferential attachment tree in distribution. And again, this tree T infinity here is essentially the limit as k goes to infinity. So essentially your infinitely large tree that you obtain by running this branching process. Okay, so quite a bit of notation. So I just want to stop here and check if there's any questions. Notation will get a little bit lighter from here, so don't worry. But I just want to make sure we're all on board. Okay, that sounds good. Right, so we have these interbirth times that are exponentially distributed, and we'll make the following 2 assumptions on the function f. First, we're going to assume that there exists some global minimizing weight, meaning that for any j and w, f of j and w is going to be at least f of j and w star. And this is sort of a technical condition that made a lot of things for us a little bit easier. It's not entirely clear to us if we can remove it, but there we go. So let's just assume this is true for now. And then secondly, we want to consider this superlinear setting. So we're going to assume that this summability condition is satisfied. And in particular, because of our global minimizing weight W star, this condition is also true if I would replace it with any other W, right? So immediately we can make the following observation because of this assumption. If we look at the sum of all interbirth times of some individual U, and we take its expected value, because this XUJ have exponential distributions, the mean of XUJ conditionally on its weight will be 1 over this function f. And because of our global minimizing assumption here, we have an upper bound that is equal to this sum, which we assumed to be finite. So this means that an individual U will only need a finite amount of time to produce an infinite number of children. So individuals will produce infinitely many children in finite time, and in particular, this time tau infinity at which the branching process is infinitely large is also finite, almost surely. So it's quite an extreme branching process, rather different from, say, a discrete time branching process that we learn in our probability courses, where you see an exponential growth of the branching process over time. That is not the case here. So this branching process really explodes. It grows infinitely large in finite time, almost surely. Okay. So this assumption that we have these exponential interbirth times is necessary to be able to discuss or this equivalence between these branching processes and the superlinear preferential attachment tree. But if you want to understand these branching processes, then assuming that they are exponentially distributed is not really necessary at all. And we can allow for much more general interbirth times, XUJ. And so that's what we'll do as we move forward. We're going to think about these branching processes with these rather general interbirth times XUJ, formulate some understanding and some theorems perhaps, and then finally we'll move back by plugging in these exponential interbirth times and see what this then means for these superlinear preferential attachment models. Okay. Of course, we're going to do this under the assumption that these sums of interbirth times still have a finite mean, so that individuals still explode. So we're still in this explosive branching process regime, if you will. Okay. So I want to mention some previous work that has looked at some of these models. One is a work of almost 20 years ago by Roberto Oliveira and Joel Spencer. They considered these interbirth times that were exponentially distributed. So they really were thinking of a superlinear preferential attachment tree, but there's no fitness here. And they had this specific choice that the rate increases like j to the power p, where p is larger than 1. And what they were able to show is that if you look at this limiting infinite tree, that it is quite extreme, because even though the tree itself is infinitely large, it contains a unique vertex that has an infinite degree, and all other vertices only have a finite degree. At the same time, it's a very short tree because it has a finite height. So the distance from the root to all leaves is going to be finite, almost surely. This is very different from the linear setting that Marcel discussed. If you would use this embedding and create a branching process that corresponds to a linear preferential attachment, then in your infinite tree, every vertex will have an infinite degree, and you will have infinitely many paths that are infinitely long. But because we are now in this explosive regime, you really get completely different and very, very, very extreme behavior. And finally, they had some very detailed results on further substructures. So some tree T will appear as a subtree of this infinite limiting tree T infinity infinitely often, if and only if this condition is satisfied. So in particular, that means that if the size of your tree is going to be too large, then the right-hand side will fall below this value of P that you have chosen, your favorite value of P larger 1, say. And so that means that in this infinite tree, you will only see very small trees infinitely often, and large trees will only appear as subtrees finitely often. Okay. Then very, very recently, a couple of weeks ago, there was a separate work by Tejas Iyer, who will appear further in this presentation as well. So he studied a much more general setting. Again, exponential interbirth times, but a very general attractiveness function f that satisfies this superlinear condition. And then also some additional technical condition that is on the right here, where this kappa is some positive constant. And he was able to show that in all such cases, you will have a unique vertex of infinite degree almost surely. And so what Tejas and I did, well, it actually appeared before this work, but what we were interested in was what can be said in this more general case. So if you move away from these exponential interbirth times and you add this fitness, which, as Marcel already discussed often in his talk, sort of introduces more competition between vertices in the tree, or in this case, competition between individuals in the branching process, then what happened? What else can we say in such a setting? So that's what we set out to answer. And the idea is that in this most general setup, we can, under certain assumptions, prove similar structural properties of this limiting infinite tree T infinity. And so the most global assumptions that we'll work under are first that if you look at these weights and interbirth times of different individuals in this Ulam-Harris tree, these are all going to be IID. So the weights will be independent of one another, and the interbirth times of different individuals will also be independent. This is nice. We're probabilists. We like our independence. So let's assume it that way. And then finally, these interbirth times, they can, of course, all depend on this vertex weight. So mutually speaking, these interbirth times may not be completely independent. But if you condition that the weight of an individual WU is equal to some small w, and that's what this lower index W here indicates. So once you condition on the value of the weight, then we want these interbirth times to become independent once more. And then finally, we of course want our branching process to be able to survive, to actually grow infinitely large with positive probability. Otherwise, there's not much we can say about the limiting infinite tree because it doesn't exist. And conditionally on survival, we want to be in this explosive regime. So this tau infinity, the time at which this branching process has grown infinitely large, we want that to be finite almost surely. Okay. So our most general results consider a dichotomy between stars and paths. So what do I mean with a star or an infinite star? That's an individual that has an infinite number of children. And what do I mean with a path or infinite path? That is a genealogical path, if you will, that is infinitely long through all possible generations in this Ulam-Harris tree. And we want to find some kind of dichotomy between the appearance of these two structures in our tree. So we remember this tau infinity to be the explosion time, the moment at which the branching process grows infinitely large. Now, let us also define tau infinity of u, which we'll call the explosion time of u. And it is the sum of two things. It's the birth time of u, and then the sum of all the interbirth times that are associated with the individual u. So this is the moment in time at which u has been born and then has produced an infinite number of children. Now, clearly, if u has an infinite number of children, then the entire branching process is also infinitely large. So it must be true that tau infinity is at most tau infinity u for any u, and hence you can take the infimum on the right-hand side to still have this inequality. And it turns out that under fairly mild assumptions that I'll come back to later, you can actually prove that this is not just an upper bound, but actually an equality. And with this equality, we can distinguish two different cases. First, suppose that there exists some individual V star that satisfies that its explosion time equals this infimum. Well, then it must be true that in the infinite branching process, this individual V star has an infinite number of children, and thus we see an infinite star in our branching process. On the other hand, if for all individuals V, it is true that the explosion time, tau infinity of V, is strictly larger than this infimum, then no individual has an infinite number of children by the time that this tree is infinitely large. So we have an infinitely large tree, which is locally finite, and so Koenig's lemma then tells us that there must be an infinite path. Okay, so we have this dichotomy of these two things. Either you see infinite stars or you see infinite paths. But the interesting question is, of course, which of these two things happens, when, and why? So that's what we want to look into a bit further. So let's consider these infinite stars first. And for this, Tejas and I came up with a new sort of idea of analyzing or thinking about these continuous time branching processes that explode. And we defined the following concept. So we say that some vertex U, which we'll think of as child number U1 of the root, then child number U2 of that individual, child number U3 of that individual, etc., etc. We say that this individual explodes before all of its ancestors if the following is satisfied. If the explosion time of U, the moment when U has produced an infinite number of children, is smaller than the explosion time of all its ancestors. So you have this individual U, you trace its path, its ancestral path back to the root, and out of all the vertices or individuals on this path, U is the first one to produce an infinite number of children. And by that time, all of the ancestors have only produced a finite number of children. And let us say that A is the set of all individuals in the Ulam-Harris tree that satisfy this condition, that explode before all of their ancestors. It is then true that this infimum over all explosion times, of all individuals, can actually be reduced to just the infimum over this set A. And that's not so hard to see. Suppose that you take some individual V who is not in this set A, then if we can find another individual who explodes before V and also is in A, then we are done. So by the definition of exploding before all your ancestors, if V is not in A, then there must be an ancestor, say V prime, who explodes before V. And if V prime is in A, then we are done. If not, you can find yet another ancestor, V double prime, who explodes even before that. And because we can only go down in this ancestral line so much, only a finite number of steps, this algorithm must terminate. And of course, one thing to note is that the root is always in A, because the root has no ancestors. Okay, so indeed, this reduction to just this set A is true. So now we can observe that if this set A is finite, if only finitely many individuals explode before their ancestors, then this infimum is in fact satisfied or attained by one of the elements in this set A. So then there indeed exists some individual V star for which we have this, for which we are in this regime of this infinite star. So if you want to know if an infinite star can appear, then proving that this set A is finite almost surely is what you want to do. So that's the name of the game. And that is the content of the next theorem. Tejas and I first proved one version of this theorem quite a while back. And then this morning I placed a paper on the archive that improves on that a little bit. And that is the most recent form that I'll present today. So we're going to make some assumptions on these interbirth times, of course, because we can't deal with this in complete generality. So the idea is we present some assumptions, and under these assumptions, we prove that what we are interested in is indeed true. So first, we want a sequence of random variables yn to exist. These will have finite mean, such that the following is true. Now, what does this mean? We recall that this quantity here is the interbirth time between child number I-1 and child number I of an individual. And this is conditionally on the vertex weight, or the individual's fitness, being equal to small w. And if we now sum over all these interbirth times from n+1 to infinity, this then means that this is the amount of time after you've already produced n children, then this is the amount of time you will still need to produce an infinite number of children. So this is, if you will, the remaining time until you explode. And we want this remaining time essentially to be bounded by some random variable yn. And we want this to be true uniformly for your weight. No matter how big or how small your weight is, you will never have to wait longer than yn, essentially. Okay. Then secondly, a somewhat scary condition perhaps, there exists some sequence lambda n that increases and diverges, such that this sum is finite. Let's not think about this too much. What I essentially want to say here is that this each term in this sum is a probability of some event, so that Borel-Cantelli tells us that only finitely many of these events will occur almost surely. So what are these events that we are interested in? The events with index n, say En, is the event that if you produce children, that your nth child will explode before you do. So you are giving birth to children, you give birth to, say, your millionth child, and now you both start producing children. Now this millionth child is able to produce an infinite number of children before you do. Well, we want this to happen only finitely often, so each individual only produces a finite number of children that are actually able to outcompete their parent. And this is kind of the crucial assumption that we use to then argue that in the entire Ulam-Harris tree, there are only finitely many individuals that explode before all of their ancestors. Okay, and finally, some technical conditions that we use to rule out some trivial cases. So first, we want this expected value to be smaller than 1. What does that mean? Well, this is the number of children that an individual will give birth to instantaneously. So this individual is born, and then in time 0, it will immediately also produce children. Well, we don't want this to be too large, because, for example, if this mean would be larger than 1 instead, then with positive probability, an infinitely large branching process just appears instantaneously at time 0. So that's not something we were particularly interested in, so we wanted to avoid this from happening. And also we wanted the following to be true. So no matter how many children someone has produced, the remaining time until explosion is always going to be positive. So it's not possible that someone gives birth to, say, 1,000 children and then instantaneously it produces an infinite number of children. And this is true no matter how many children you have already produced. So these trivial cases we wanted to avoid. And one thing to note perhaps is that if your interbirth times have, say, an exponential distribution, so a distribution that has no atom at 0, then this condition C is trivially satisfied. So if you just want to think about these interbirth times in terms of these exponential random variables to be able to link it back to preferential attachment, then you need not worry about this condition C at all. Okay, so the idea is that under all these conditions, we can then prove that this limiting tree T infinity indeed contains an infinite star almost surely. Okay, then what about these paths? So in this regime here, well, suppose that the following is true. Suppose that for each individual, we can find some random index I, such that individual ui, which is child number I of u, produces an infinite number of children before u does. And we can find such an index or such a child for each individual u in the Ulam-Harris tree. Well, then by contradiction, we can very quickly argue that there must be an infinite path, because suppose that there exists some v, whose explosion time equals this infimum, so that we would be in this infinite star regime. Well, clearly this can't be, because if v equals this infimum, then the explosion time of vi is strictly less than the infimum. Well, that's not possible. So we have a contradiction, and so our assumption here was in fact incorrect. And so rather, we're in this infinite path case where no one's explosion time attains this infimum. Okay, so again, we can prove that this condition Here, this is the crucial condition that you can find a child who explodes before you. We can prove when this happens almost surely. So again, the name of the game is find some conditions for these interbirth times such that this is true. And here we want there to exist certain numbers mu that depend on I and W such that the following conditions are satisfied. These again look not so friendly, but let me take a bit of time to provide some intuition. So suppose that we have some individual, say U, and we're going to condition on the weight of this individual U being small w. Okay, then we look here at this sum, this tail sum of interbirth times, conditionally on the weight being small w. So this is the case when U has already produced its ith child, and now this sum here tells us how much longer we need to wait until U explodes, until U produces an infinite number of children. Well, this probability tells us, or this event tells us, that we need to wait at least mu IW amount of time until U explodes. And the condition here is that this lim_inf of this probability is strictly positive, so that essentially this probability is uniformly bounded from below in I. That's not exactly what it says, of course, but let's just assume it is, just for the sake of argument. So for each child that you produce, the amount of time that you need until you produce an infinite number of children is at least mu of IW, with some probability, say at least delta, which is strictly larger than 0, and delta does not depend on I. At the same time, we have this first condition here, and this infinite sum here we will think of as the time that I needs after it is born to produce an infinite number of children itself. And this event tells us that vertex I needs less than mu IW time to explode. So if U has produced its ith child and then still needs mu IW time to explode, but this child I itself needs less than mu IW time, then it is clear that this individual I will win from its parent. It will explode before U. And this sum being infinite here tells us that by the reverse Borel-Cantelli lemma, we will find infinitely many of such children. So infinitely many children will need less than mu IW time to explode, whereas with probability uniformly bounded from below, the parent will every time need at least mu IW time to explode after producing I children. And so this is what we use to show that indeed you can find a child always that explodes before its parent. So in this case, we can conclude that this tree T infinity contains an infinite path. Okay. Now, these conditions for stars and paths may look completely disjoint, completely separate, but the idea is that once we start to apply them to these superlinear preferential attachment trees, that we actually see that they are quite close together. And that's what I'd like to do. One final thing, we have shown now that there are regimes when there exists stars, there are regimes when there exists paths, but we've not said anything about uniqueness or whether we can exclude that there is a star and a path. I don't want to spend too much time on that, but rather just say, if you assume that your interbirth times have a sufficiently smooth distribution, so say, for example, an exponential distribution, then you will always have uniqueness. So there will always be a unique star, there will always be a unique infinite path, and they will never appear together. Okay, so let's go back to these superlinear preferential attachment trees. So a quick reminder, we now assume that these interbirth times have these exponential distributions, and we assume for F that we had this global minimizing weight W star, and we had this summability condition, right? So these are the three things to keep in mind. Okay, then let's look at these conditions that we had in our theorem for a star. So first, we needed some random variable yn, and we're going to take that as a sum of exponential random variables with exactly these rates, with this attractiveness function f and this global minimizing weight W star. Then it is indeed true that this tail sum of interbirth times is stochastically dominated by Yn. Why is this true? Well, first we chose our interbirth times to have an exponential distribution. Then we had this global minima for the function f. So these rates of Yn are always going to be at most f of j minus 1, comma w for any other w. And so we have this stochastic domination. And by this third condition here, we know that Yn actually has a finite mean. Okay, so that's all done. Then there was this scary sum. Well, it'll still be scary if we apply it to this exponential interbirth times, I suppose. But at least we can do some calculations. Since Yn is a sum of exponentials, this expected value will become a product. And again, here we have again a sum of exponentials, so this will all turn into products. So it's rather a sum of products that we want to show is finite for some choice of your fitness distribution and some choice of this sequence lambda n. And though I'm not going to show you how to do this, this is a tricky but technical exercise, I suppose. But what I just want to highlight is that we can choose often this lambda n to be some small constant delta times the expected value of this Yn divided to the power minus 1 times log n. That's what we can often use to show this condition B. On the other side, we have the conditions for a path, and we'll skip some details here, but the idea here is that we can prove that the conditions are met if there exists some constant c larger 1 such that this sum of products is infinite. So this indeed doesn't look so much different from the condition for a star, which was this sort of crucial assumption B. And so they almost look like a converse. We still have an infinite product, but here this infinite product has been taken out of the expected value, and here we have a minus rather than a plus. And here we have a term with a constant c larger than 1, whereas this lambda n has a constant delta that we want to be able to choose as small as we need. So they are not exactly, it's not an if and only if situation here. We haven't been able to exactly prove that, but it shows that these sufficient conditions for a star and a path are actually quite close, and that the gap in which you would not be able to say anything about a model is not so large. And indeed, that is what I would like to highlight in a couple of examples to round it all off, and then we'll be done. Okay, so a first example is similar to the models that Marcel talked about, in the sense that we can kind of factorize our degree and our fitness influence. So our function f is now going to be some function s that depends only on the degree, and we have some multiplicative function g and some additive function h that only depend on the fitness or the weight variables. And so we'll choose for this function function h to be a polynomial, so w to the power gamma. We'll choose g to just be a linear function times a slowly varying function, L1. If you do not know or can't remember what a slowly varying function is, just forget it exists. And for the degree function s, well, let's take this example that we've seen a couple of times, this I to the power p, where p is larger 1, and again, L2 is some slowly varying function. And then for the weights, we'll, as we saw in Marcel's talk, we'll take a power law distribution. Okay, so in this setup, we can prove exactly when we will see this unique infinite star in our superlinear preferential attachment tree, or rather an infinite path. But let me provide a little bit of distribution or of intuition regarding this model. So this constant p here, this parameter p, is going to tell us how much competition there can be between old and young individuals. Suppose that you have the root, which has been producing children for quite some time, and then much later, some individual U is born. Well, if the root already has a lot of children, then especially if P is large, because of this quantity, it is going to be producing new children at a very high rate, so very quickly. Whereas this individual U, who has no children yet, still needs to sort of start up and get going and produces children very slowly. So the likelihood that this vertex U is able to outcompete the root is not very high, and the larger you choose P, the less likely this becomes. The same is true for alpha. If you choose alpha very large, then there's not going to be a lot of individuals with a very heavy weight. And this large heavy weight would also help them to produce children very quickly and compete with, say, this root individual. So the larger P, the larger alpha, the less competition you will see. But on the other hand, the larger you choose gamma, the more competition you will see, because a large gamma actually helps individuals that have a large weight to produce children at a very high rate. And that is exactly what we see reflected in our result, that this infinite 3T infinity will contain a unique infinite star when this inequality is satisfied. So as long as either P or alpha is large enough or gamma is small enough, then you will see an infinite star. So exactly this confirms our intuition that you need to choose these parameters in such a way that there is not enough competition for these young individuals to win. So this you could think of as the weak disorder regime that Marcel discussed in some way in this setup. On the other hand, if you flip the inequality, then you will see a unique infinite path almost surely. So here we see that even though these sufficient conditions were not exactly an if and only if thing, that they are strong enough to still provide us with an exact phase or precise phase transition here for such an example. Okay, let's look at a second example. So we'll forget about these additive weights now and just take multiplicative weights. So we'll take them to be linear. And for this function f, we're now going to choose something that grows very, very slowly, faster than linear, but only just fast enough to still satisfy this summability condition, that this sum over these 1 over FIW is going to be finite. Right? This is satisfied, but it really does grow very, very slowly. Okay. So for the weights, we're going to do a lot of exponentiation. We don't need such heavy weights in this case. So the tail will be decaying like e to the minus e to the x to the kappa. So something that decays rather quickly. And again, the intuition here is that the larger sigma is, the less competition there is, the stronger these old individuals with large offspring will be compared to young individuals. And similarly, the larger kappa, the faster your tail decay of your fitness function, fitness distribution, the fewer large weights you will see that could help competition arise. And again, this is exactly reflected in this theorem in the sense that you see a unique infinite star in your limiting infinite tree, only if sigma times kappa is larger than 1, and on the other hand, if it's less than 1, you'll see a unique infinite path. Okay. And finally, I want to come back to this case when there is no fitness, because there were some results already that I mentioned earlier by Oliveira and Spencer, and also by Ayer. So we'll assume that the function f only depends on the degree. And we saw that Tages had this nice general theorem where you had this superlinear condition and then this technical condition over here. But you can think of choices of f that satisfy the first condition, but not the second. So for example, this one over here. You essentially always have a rate that grows much faster than linear, but every now and then, when your j is a perfect square, so j squared, the square root of j is going to be an integer, then you give it a much, much smaller value. So say j to the beta. So every now and then, an individual needs to wait much longer to give birth to the next child. Well, this messes up this monotonicity condition here, because every time that n is such that the square root of n is an integer, this right-hand side is going to be very small, but the maximum on the left-hand side will still be very big. Okay, well, under these new conditions, under this more general theorem, we can indeed still work with such examples. So we can still prove that in such a case, you still see a unique infinite star almost surely. And in fact, we can devise conditions where you actually have a whole family of such functions f for which we can still prove such behavior. But we're not quite there yet in terms of complete generality, where you only need this summability condition. Okay, so that's all I'd like to say. Just a little bit of open problems and a lookout for future work. So the big open problem for me is whether we can prove whether such a unique infinite star emerges under only this summability condition in the case that there is no fitness. So we're getting closer and closer, chipping away, making things more general, weakening conditions, but we're not quite there yet. And the question is that a technical inability, or is that really an understanding, something that we're not looking at that could still be improved? And in the case that there is fitness, in particular when you have this infinite path setting, we know that on this path, individuals must explode quicker than their parent, and quicker and quicker and quicker. So on this long path, where do you then find individuals with a very large degree? That is something that is not very clear. Understanding these infinite paths and their structure is still quite hard. So that's something we'd like to look into as well. And in particular, what can you say about the height of these trees in this infinite path case? So when there is an infinite star, your height will be finite almost surely. But in the case of this infinite path, how quickly does your height of the tree grow? And some current ongoing work is again in the setting with no fitness, where we wonder what happens if vertices explode not almost surely, but with a probability that is not 0, but also not 1. So not everyone perhaps explodes, only a fixed finite proportion of all vertices will actually produce an infinite number of children. So what happens there? And it turns out that then you open up a whole new can of worms of interesting behavior. So thank you very much for your attention. If you thought this was an interesting presentation, then have a look at the paper by Tejas and myself on the left here, and the one that came on the archive just today on the right by just me. So thank you very much, and I'd be happy to answer any questions you have.
Yeah, thanks, Bas, for a really nice talk. So again, if there are any questions, feel free to just unmute yourself. Raise your hand. Otherwise, okay, if not, maybe let me go on with the first question. So assume you're in the setup where you really can talk about your explosion time for like the CMJ processes.
Yeah.
Can you say something when you condition on this time being extremely large, somehow saying like larger than some constant m and sending m to infinity? Could you say something then about somehow what happens like way before this explosion time? Is there? Because in some sense that feels like, okay, there's like this infinite bit and there's like the finite bit before. Is there something you can say?
Yeah. Well, we've never thought about it, so I'm very much on the spot right now, I'd say.
Okay.
But of course, so if you think about, for example, this exploding of an individual, that they produce an infinite number of children. I mean, what happens there essentially is that there is some randomness in the beginning, and after a while, you are producing children at such a high rate that it's almost deterministic. So you have sort of concentration of the remaining amount of time after you have produced, say, n children until you explode, and that time concentrates around the expected amount of time. So if you have to condition that this takes very long, then what you essentially see is that barely anything happens, because if you want the explosion time of an individual to be long, what that means is that it's going to be stuck at some point where it has given birth to, say, k many children, and that is exactly where the rate of the exponential distribution, at least in the exponential situation, where the rate is smallest. So that is the most likely way in which you have to wait a very long time, is just that this individual gets stuck at this number of children. For an infinite path, I have less of a good intuition what that would mean. Then I think it's sort of a a cumulative effect that adds on throughout the generations, because to be able to produce this infinite path, you have to find these extremely lucky individuals that can produce children very quickly, one after the other. So if you condition that to take a very long time, then you will just not find these lucky individuals, and instead you have to wait very long before each individual sort of gets started with producing a lot of children. So I think that would be the sort of the main thing, that everything sort of takes a much longer time to get started, but then eventually it'll be the same. But how exactly that sort of turns out, I couldn't tell you. But it's an interesting question.
Yeah, some of the thought was maybe you can, like, by this conditioning, tell apart whether you see star paths, maybe something like this.
Right. Yeah. Yeah, that I don't know. That's a good point. Yeah. Thanks. Interesting.
Okay. Any
Something
more
in the chat.
questions? Marcel?
Yeah, so thanks for the response. So you had this condition that your fitness had to be sort of lower bounded by a particular fitness value or your function. So what can go wrong if you don't have that? I mean, is this
Yes. Yeah, good question. Good question. So there is this global minimizing
yeah,
condition that we had, right?
yeah,
Where was it? Yes, here. Gone past it already. Right. So here we had this global minimization condition. Is that what you meant?
yes.
Yes. So take, for example, let's see. Take, for example, f of j comma w is, say, w times j to the p, where p is larger than 1.
Right.
So you would still have some kind of global minimizing, because you could choose w star equal to 0. But okay, something that I suppose forgot to mention here is that we want this rate to be strictly larger than 0, this f of jw.
Okay, I see.
So this is not satisfied in this case.
Yeah.
What that essentially means is that it is going to be impossible to satisfy this condition over here, this one, where you kind of can say that uniformly in your choice of your weight, you will always explode at least as fast as this random variable yn dictates. But if you can choose if you can essentially be arbitrarily unfit, then you can always find individuals that will take longer and longer and longer to explode. And that was sort of a technical issue that we had. So you have to sort of intuitively, you have to stay away from the case where individuals can be arbitrarily unfit and thus can take arbitrarily long to explode, exactly because it takes so long before they even produce a first child, say.
Yeah.
And this was difficult for us to handle, because the idea is you want to show that the number of individuals that explode before all their ancestors is finite. But if you happen to find this case where you find an individual and all of its ancestors have just such small weights that it's almost impossible for this individual to lose, then that exactly hurts us in the way that we don't want. So if all of these ancestors explode at least as fast as this random variable yn, then we can somehow control that it's then unlikely for these very young individuals to win. Whereas if all these ancestors could be arbitrarily unlucky, in a sense, then that would cause troubles.
Okay.
But there's probably a way around it, and at some point we just said, okay, let's assume this for now, and then we can think about that later, but never came back to it.
Thanks.
Okay, right. Any more questions? Comments? Doesn't seem to be the case. So let's thank both speakers again. So yeah, thanks a lot. And maybe already as an announcement, like the next seminar will be in 2 weeks by talks of Patrick Ferrari and Alessandro Uccelli. So yeah, see you then next week. Or 2 weeks, sorry.